right. We got David Engelhardt in the house. We have Mr. Hofken and Steve. Welcome, everybody. So, I got caught up on another task, and I didn't realize what time it was. And it is time for IAEI News Live. And today we're going to talk about motors. We're going to dig into motors, and probably for the next few sessions, we are going to do a deep dive in through Article 430, motors, motor protection. Laurel, get ready, because IAEI News Live, motors, motor protection, motor conductors, ampacity, all that jazz, and it all starts now. Oh my gosh, I don't know about you guys. Redondo, I need coffee, and all I got right now is agua. And I am, my coffee pot is over there, and I forgot to make my cup because, like I said earlier, I got completely engrossed in another topic. And then I looked at my clock and I'm like, oh my goodness, I gotta go live. I'm missing it. And we can't miss another IAEI News Live. So here's my thoughts. Motors, and I know we got in a little bit into this. I think we did. I can't remember anymore. When it comes to motors, there's some fundamental things that I believe we want to make sure that we capture. Hey, Willie Snyder, happy Tech Tuesday, brother from another mother. All right, so I am going to just set this up. There's a few points that when it comes to motor circuits, template settings, when it comes to motor circuits, we have to remember that there's a couple things that we do differently with a motor circuit. One of the major ones that I think is critical to understand is that when we establish an infrastructure, get your coffee pot started. Get your coffee pot started. Yes, it'll be okay to take that time. I know, but I gotta clean the pot. We're gonna go. You're gonna get me sober. So, so when I think about a motor circuit, and what's I think a little bit different than other applications, is that when we build the infrastructure. So if you think about, and I don't know if this is gonna work. I didn't try it, and it works. So if I think about an infrastructure, I have a motor. Look at that nice circle. I have a motor, and we know that we typically are going to have what? I don't know how to draw this. An overload, and then we have a contactor, and then we'll have, we got a disconnect in here, right? So I am going to put the disconnect right here. So we have a disconnect, we have a motor, we have a disconnect for the motor, and I'm going to say that this, oh, that was a bad color. That is a, I'm gonna call this like your motor starter. And now we may have a drive, all that good jazz. Then we'll come up to an overcurrent protective device and a bus. I mean, that's typically the motor circuit. When I think about the infrastructure of the motor circuit, this component right here, that component we want to be replaceable. We want the conductor and the overcurrent protective device, and I would say we want the disconnect to handle different motors. And when I say different motors, what I mean is if I have a 5 horsepower motor and I replace it with another 5 horsepower motor, I don't want to have to say, well, I can't use that horsepower, I can't use that specific motor because the full load amps is different than the previous. If I design it around the nameplate of the motor, the infrastructure, then I'm challenged whenever I'm replacing motors in the future, and we'll probably do that. So, and the overloads, and now the overload needs to be matched with the motor itself because that's the piece of the protection level for overload protection that would be changeable in the field, maybe adjustable via a set point, or maybe changeable being meaning I can take the element out and put the other element in. So I think the point is that when we approach a motor circuit, there are components of the motor circuit that we will select not based upon the motor that we have, but based upon a table, okay, that's in the National Electrical Code. Sort of like the standard ampere ratings in Article 240, where we'll say, well, these are the standard ampere ratings for overcurrent protected devices. Might I get a manufacturer that designs a circuit breaker that's in between those values? Sure, but I just can't use them when the code says the next larger size because I've got to go back to that table. So I think it's similar. Yes, that's right. The 2026 NFPA 70 is on NFPA link as we speak. So you can go out to NFPA link and grab the 2026 edition of the National Electrical Code, and that little click of my finger hurt so bad because I'm ashamed to say it, but I'm not. I almost cut my finger off the other day, a little bit ago, a couple weeks ago actually, because I was using an angle grinder. I was using a grinder, one of those DeWalt grinders, and it slipped out of my hand, and the guard was on the other side, and it caught my finger. And I'll tell you what, ooh, doggy, it took a chunk of skin out. But it is healing up, but it is still aching me right now. So Laurel, yes, it is available. Willie Snyder says, it's crazy watching a chop saw motor spike 50 amps on a 20 amp circuit just for a split second. Yes, and that shouldn't trip your overloads and your overcurrent protection, right, Willie? And that's the whole point, I believe, of when we size the infrastructure for these applications. So when I'm looking at my motor, when I'm looking at my motor circuit, I have my overcurrent protected device that's protecting giving me my short circuit and ground fault protection. And then I have a conductor, I have a motor starter, which I could say, you know, this may be a variable frequency drive. I might have different solutions there. So I'm sizing the infrastructure, and where do we get that from? We get that, boom, 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 boom. In Article 430, early on in Article 430, and I don't think I'm showing it, good. Early on in Article 430, in 430.6, we say that the size of conductors supplying equipment covered by this article shall be selected from the ampacity tables in 310.15. And remember, 310.15, if we go back to 310.15, this is where you're going to find your ambient correction factors and your number of conductors in a raceway. So just because when you're selecting your conductors, you still have to think about the ampacity of the conductor. And what is ampacity of a conductor? The ampacity of the conductor is a defined term. We can go to Article 100, and here's a nice feature I love about NFPA Link. Not only can you now get the 2026 edition of the National Electrical Code, but you can open an entire article in its own tab and have multiple instances, and you don't have to keep all the way around. I can have multiple instances open. So now I come to ampacity, and ampacity says it's the maximum current in amperes that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. When do you think, all right, here's a quiz, Mr. Snyder and Michael Hofkin and everybody. When did the term ampacity enter the National Electrical Code? What year? What edition? What edition of the National Electrical Code did the term ampacity enter the code? And while you're figuring that, I am going to grab an older code book. So what year? I'm putting it in the chats. Come on, I need the chats. I need the chats. And while you're doing that, I'm going to just check. Yes. What year? I have the code book in front of me. Oh, and I'm showing you that it's red, and I'm showing you that it's small. So here's the back of the book. So Michael Hofkin says 1959. 1959. Do I have a 59 code book? Yes, I have a 59 code book. Willie Snyder says the 20s. Now, and before this happened, we'd called ampacity something different. We called ampacity something different. And I'm just checking the 59 code book because Mr. Hofkin probably has a library much better than I do. Well, apparently not as good because it was not in the 1959 code book. All right? Whoa. I don't know if that's... Anyway, you can't see it. I have the 1959 code book, and it's not 1959. Willie says the 20s, and if it wasn't in the 59 book, then it sure as heck wasn't in the 20s. I can tell you what we called... Let's first talk about Article 310 in the... Michael Hofkin says it's in there. So let's go to 310. Well, my question technically was, Michael, when was the defined term entered? So if I go to 310, they did not use the term ampacity in the code book in 1959. In 1962, you're probably right. That's when they started that transition. And then in 65, they created the formal definition in Article 100. Before 62, in the 1959 code, they called it current carrying capacity. And current carrying capacity was not a defined term, but that's what they referenced it in Article 310. The maximum continuous current carrying capacities of copper conductors. And they didn't have 90 degrees C conductors back then either, right? It was all 75 degrees C. So, and I just had that discussion. There's no THHN. And I would love to know your guys' and gals' thoughts on when did THHN? When did that hit the market? Because back in the 50s, we did not have THHN conductors. There was nothing in there. They had thermoplastic, they had asbestos. Woo, haven't seen asbestos insulation in a long time. We had RHH, THW. So in any case, the tables were pretty much the same. So ampacity is the ability of a conductor to carry current without damaging itself. And when you look at the tables in 310.16, let's go to 310.16. When you look in chapter 3, walk with me if you will. Watch this, watch this, watch this. I'm right mouse clicking and I'm going open a new tab. And then I have a tab here to open. So I can go to this and see Article 310. I can click here, go to Chapter 1, Article 100, and I have a tab here for Article 430. Isn't that the cat's meow? That's why everybody needs to get NFPA freaking link. I mean, give me a break. All right, NFPA, then I look at 310.16. Now this table, okay, so here's the thing about this table. The values that are in this table are the currents that these conductors can handle. If I have a 90 C insulated conductor, that means I can handle, say it's a number 8. I can handle 55 amps as long as I have not more than 3 current carrying conductors in a raceway. And if I go to the notes, as long as the ambient temperature is not other than 86 or not greater than 86 degrees Fahrenheit. And then there's a range in there, and cooler values, I can put more current through there because I'm cooling the conductors off. But in any case, even a number 18, small conductors, I can put 14 amps through a number 18. Let's take a look at table 310.16 in the next edition, which will be the 2026 edition, NFPA 70 2026. Look at this. I go to chapter 3, I go to Article 310, we go to 310.16, and this table has changed. Let's take a look at what this says now. I have 16, look at this, we filled in more blanks. I've got 16 and 14, let's take a look at the previous, or the current edition. I've got down to an 18, 16, 14. In the 2026, I don't have an 18, I got 16, 14, 12, and 10. So, and I have values for 16s and 14s. But if I look at the 2026 edition, a number 14 can handle 25 amps all day, all night, as long as it's a 90 C insulated conductor. So what that tells me, I have small conductor protection requirements over in Chapter 2. In 240, but that's not going to apply over here in Chapter 4. I can use those smaller conductors for motor applications, and I don't need to follow the small conductor protection. I can follow this as it is in Article 430. And what gives me the right to do that? If you go to Article 240, and I'm going to do it again, right mouse click, open in a new tab, landing on your face, there's Article 240, and look at this. Other articles, it references Article 430 in here somewhere. I know it's in here, I don't know where, here it is. Motors and motor circuits. Now this is equipment can be protected against overcurrent, but I'm worried about conductors, right? Because it's small conductors. I go to 240.4 for protection of conductors, makes sense. And if I scroll on down past the small conductors and I go to overcurrent protection for specific conductors shall be permitted to be provided as referenced in 240.4G, the table. Here is the table, and when we see motor operated appliances, motor and motor control circuit conductors, Article 430. So Article 240 is giving up the purview of protecting motor circuit conductors because they specifically are telling you, look, I know all this stuff I'm telling you up here in 240.4 for protection of conductors, but you know, Ignore all that and go to these specific sections or these specific areas of the code for these specific conductors. And that's what gives us the purview in Article 430 to say, look, we're going to manage the protection of the conductor and the equipment for these motor circuits. I still have to protect the conductors. That's not going away. I still have to protect all of the components. I have to protect all of these components, right? I've got to protect everything that is in this circuit. I have to worry about that conductor. I have to worry about this motor starter. I have to worry about that contactor, this conductor, and there's another conductor in between there. So I've got to worry about all of these components. Still, it's not like I'm going to ignore the protection of the conductors. And 430.6 tells me some of my fundamental policies or rules I need to follow. For general motor applications, I'm going to reference a table. Now, why would I reference a table? What table are they talking about? Let's go to 430.247. 430.247 is the full load currents for direct current motors. 430.248 is your full load currents in amperes for single phase alternating current motors. 430.249 is your two phase and then your three phase. So your 250 is your three phase. And it tells you per horsepower and voltage a full load amp value. And you might say, well, Tom, why wouldn't I go to the nameplate of the motor? And I would say, because you're trying to build an infrastructure that can handle multiple 5 horsepower type of motors. So I'm going to design the circuit based upon these tables, not on the actual motor that I have in place. And if I look at 430.6, boom, 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 boom. If I look at 430.6, conductor ampacity and motor rating determination, it tells me when I use the table values. I'm going to use the table values when I'm selecting the ampacity of the conductors, the current ratings of switches, and the current ratings of branch circuit, short circuit, and ground fault protection. So if I go back to this, I'm going to use the table and not the actual motor nameplate when I am selecting this component, the conductors, those three, and then when do I use the nameplate values? The nameplate values are going to be used when I'm dealing with separate motor overload protection, so my motor overloads. When I have a motor that's built for low speeds, less than 1200 RPM, high torques, canned pumps, or multi-speed motors, then I'm going to use the actual motor nameplate for the ampacity of the conductor, the current rating of the switch, and the current ratings of the branch circuits. If it's not a low speed, then I'm going to use it for motor overload, and if it's a large motor, I'm going to use the nameplate value. So if it's not one of these other two conditions, I'm only using the nameplate data for my overload protection. And that's an important thing to remember. And I think, again, what you're trying to do is build an infrastructure for that motor circuit to accept, maybe to be prepared for a little bit of the future. All right, Freddie B, I got to read some of this. Did they get rid of small conductor rule? It said that a number 12 was limited to 20 amps. No, they did not. Here's the thing you got to remember, Freddie B. What you've got to remember is, I believe that is in 310 dot, is that dot 5? Dot 5. So, and I know there was an appeal Here's the 310.5 language, minimum size. The minimum size of conductors for voltage ratings up to and including 2,000 volts shall be a 16 gauge copper, 14 gauge copper clad aluminum. That's why the 18 came out. And then a number 12 aluminum. Aluminum. All right, so they did make some changes in that section, but now for a motor, there is a minimum size for a motor. What is the minimum size for a motor circuit? Can anybody out there tell me? I know what it is in my head. I'm going to look for it in the code. You tell me. 240.4G, 240.4G, 240.4G. So if I go to 240, I am in 240.4 alpha meno G, G, G. My hair spells terrific. Yeah, so 430 is there. I'm not sure. Table G, I already talked about table G. Takes me out of Article 240 and puts me over. So what is the minimum size, though, for a motor circuit? There is a minimum size. Where is it? I know what it is, but I got to find it. Anybody out there know? What is the minimum size conductor for a motor circuit? I'm not going to tell you until you tell me. I'm going to look for the section. Come on. Part winding other than continuous. Here we go. I found it. Found it. David Engelhardt says, yep, 125% of the table, full load current. I agree with you, David, but there is a minimum size conductor that you have a minimum size. Willie Snyder hits it. There is a minimum size, but you can use an 18 or a 16 under specific conditions. But the general conductor for small motors shall not be smaller than a 14 gauge unless it's permitted in 430.22 G1 and G2. G1 is an 18. Now the question is, in the 2026, did they remove the 18 from 430.22? Columbus sailed the ocean blue. Let's take a look. 430.20, 22, 4, 3, 430. 430 is triente, right? Triente? 22. 430.22, it's still there. So conductors for small motors shall not be smaller than a 14 gauge unless otherwise permitted in G1 or G2, but they took the ampacity of the 18 out of table 310.16. I don't know how that's going to work. But in any case, your minimum size, you're typically going to go to a 14, all right? All right, so the infrastructure is important, and we're covering 430.6 conductors. We talked about the nameplate values, when to use the nameplate values. Torque. When you have a torque motor, you know you're going to be, your locked rotor, you're going to be driven off of the locked rotor amps. So what they're doing in 430.6, again, is they're laying that foundation to make sure that you have an infrastructure that doesn't have to change if you change that motor. At least that's my opinion. That's the way those are the tea leaves I'm reading based upon the code requirements. They talk about an alternating current adjustable voltage motor. They address the worst case scenario. They tell you that the maximum operating current does not appear on if the maximum operating current doesn't appear on the nameplate, then you have to determine the current rating based upon 150% of the values given in the two tables. And then they have valve actuator motor assemblies. Freddie B, 240.4D. Yes, so 240.4, we're going to talk a little bit about 2026. Panel 10 made a change to 240.4D for small conductors. I wouldn't say that it's all been rewritten. I think we reorganized it a bit. We made some adjustments, but we're all good. I don't believe there's I don't believe there's major technical changes that are there. You'd have to really take a look and compare, but I don't believe we intentionally made any major technical changes outside of rewording and restructuring. That table specifies the specific application conductor sections where they have different requirements than general, such as the 75 degrees C ampacity of small conductors with conditions. I think, I'm not sure if you're talking about number 12 copper, number 12 aluminum. I'm not sure what you mean by that, Willie. I don't know whose answer you're going to. But in any case, 430.6 is addressing that infrastructure for the motor application. 430.7 is going to tell you the information that you need on a nameplate, and that information should align very well with the UL standards for motors and how we list these motors. Now, I don't know that motors are required to be listed. Let me look. Let me look at the 2026 code and look at Article 430. I don't have a listing requirement for motors. Michael Hofkin, what's up with this? There's no 430.2, so does that mean that a general use motor is not required to be listed? Let's do a search in the 2026 code cycle to see if there's a listing. They got requirements for combination motor controllers, fuses, circuit breakers, motors, short circuit protectors. I don't have a requirement. Tap conductors, a listed motor circuit switch. Guys and gals out there, research, where are you? Is there a requirement that motors have to be listed? I'm not seeing it. I see a lot of listing requirements in 430 for all of those components. Willie, I would say you list it the same way you would list a transformer. Not much difference. You would have to have it meet certain performance criteria. You'd have to make sure there's probably, I would say that if I was going to list a motor, I would give it criteria. I'd have it run continuously to make sure that it doesn't overheat. I would put torque values on it to make sure that it doesn't overheat. There's probably a lot of performance criteria I could put or think of putting in the code. Yeah, and Chapter 9, Table A1A, there are a lot of UL standards in there. And Laurel, is there anything for motors? I don't think there are. I'm not aware of any. Transformers are not required to be listed either. I know, but there are transformer standards out there. There's performance requirements out there for us. And I don't see I'm not seeing anything. Yeah. So That's interesting. All right, so we don't have a listing requirement for the motor, but we have a lot of the other components associated with that, with the motor installation. All right, let's go back to 430. So it's, and because you don't have a listing requirement that drives how a motor is to be marked, you need a code requirement to say this is what is required on the nameplate. If I don't drive the products to be listed, and if I didn't have a section in the code that says this is the information you need on the nameplate, then there is nothing that tells the manufacturer they need to even tell you the full load amps. They could put whatever they want on that motor, and you would have to try to figure out how to make that work. So in 430.7, we tell you, here's what the information that you need on a motor. All right, so piece of cake. We also in 430.7 give you the locked rotor indicators, or code letters. So they'll tell you if the locked rotor is if the code is an A, B, C, or D, etc. They give us a range of kilovolt amperes per horsepower. So kilovolt amperes per horsepower with locked rotor. So how do you interpret that one? It says the code letter indicating motor input with locked rotor shall be in an individual block on the nameplate, properly designated. So it even tells you it has to be in its own little block. It can't just be in a list or in a paragraph. And it has a code letter. So it says code letter D is 4.0 to 4.49. How would you apply that? Willie, how would you apply for a code letter D 4.0 to 4.49? What does that tell us? And while you're thinking that one up, I'm going to move on. So in locked rotor, it talks about multi-speed, single speed, dual voltage, 50, 60 hertz. That's a good one. And then you have your part windings. You have your torque motors, and you have your multi-motor and combination load equipment, factory wired and not factory wired. So 430.7 is going to have, it's going to ensure that the nameplate of a motor has what we need. And from an inspection perspective, you would want to make sure that whatever data is required to be on the label on the nameplate of the motor is on that nameplate, because that information is going to be important for the proper application of the motor. Oh, so Willie's doing some homework. Class 2 transformers, yep. Class 2 transformers are required to be listed, and so some transformers are required to be listed, others are not. All that jazz. So excellent. Thanks, Willie. All right. So, and then 430.8 talks about the controllers. What are the markings for a controller? And then 430.9 deals with terminals. Now, terminations. I'll tell you what. So let me ask you a question. And I'm going to put a survey out. I am going to put a survey out on this one. I am going to put a survey out for this one. And I know we're not there yet. Motor circuit conductors is coming up, but in 430.22, let me just bring this up. I know how everybody teaches this, and I would love your guys and gals' opinion on this, because I'm doing my homework right now. 430.22 for a single motor says conductors that supply a single motor used in a continuous duty application shall have an ampacity of not less than 125% of the motor full load current rating. When you determine the ampacity of the conductor, how are you doing that? If I said that my full load amps was, I'll give you an example. Let me show you something. So if I told you my full load amps was on the, say I was a 5 horsepower motor. Let's say I'm a 5 horsepower. No, let's not do a 5 horsepower motor. Let's do a 30 horsepower motor at 460 volts. A 30 horsepower motor, that's not a good example either. I'll stick with a, I guess it's okay. Well, let's do a 5 horsepower motor with 16.7 per the table. It's 16.7 amps. 5 horsepower, 16.7 amps, full load current for a 208 volt application. And that's based upon the table. The 1.25 times 16.7 is 20.9. What size conductor would you select to meet this requirement of 430.22? Conductors that supply a single motor used in a continuous duty application shall have an ampacity of not less than 125% of the motor. And we'll say the conditions of use are 3 current carrying conductors in a raceway, and the ambient is 86 degrees. It's a quiz for you. 5 horsepower, 208 volts. What conductor would meet the requirements that has a ampacity of not less than 125% of the motor? That's a quiz. That is a quiz for all of you guys and gals. Because we're going to move right into, I'm going to go back and see what we missed while you're figuring that math out for a 5 horsepower motor, 208 volts. What is the minimum size conductor based on 430.22? While you guys and gals are doing that, marked on the motor, we talked about 430.8, we talked about 430.9, and then you have wiring space in enclosures. You got wire bending rules in 430.10, so we're working on the infrastructure. 430.11 is protection against liquids, so it has to be suitable for the application, whether it is direct spray, dripping, rain, all that jazz. You're working on a 5 horsepower motor, 208 volts. Full load current is 16.7. What size conductor would you select? 430.12 is your motor terminal housings. Talks about the construction has to be substantial, whatever substantial means in your mind. We know it has to be metal, can't be plastic, because it says where motors are provided with terminal housings, the housings shall be of metal and substantial construction. So no tin metal. Dimensions and space, they give you dimensions and space for wire-to-wire connections, etc., etc., etc. Nobody wants to take a guess at a 5 horsepower motor, 208 volts. Full load current of 16.7 amps based upon the tables. I'm not going to do it for you. I want to see, you know what? Maybe I'll do here's what I'll do. I'll do a Mentimeter. Ooh, let's do it. You guys and gals want to do a Mentimeter? That's what we'll do. I'm going to do a Mentimeter. Hold on. Hold on. Where's my Mentimeter at? I've got to set this up for the Western section. All right, so I'm going in, I'm going home, and I'm going to do new, and we're going to show a code. I'll put a link. I'm going to number 12. I got a number 12, so I'm going to do multiple choice. I'm not going to put a multiple choice. I'm going to say, is motor continuous duty? Yes, continuous duty. Continuous duty. What size? What minimum size conductor? Question mark. And I'm going to say 5 horsepower continuous duty, 208 volts, 1.15 service factor, all standard stuff. Full load current of 16.7 amps based on table. Conditions of use for the conductor align with table 310.16. And I'll do, what do I want to do? I'm doing multiple choice, so I got to do multiple choice. I'm doing multiple choice. What's the minimum size conductor? We'll do 12, 14, 10. So those are my, I'll just do 12, 14, 10. Or should, yeah, no, I should do the smallest one. 14, 12, or 10. All right, so let's do this. Share, multiple choice, save. I'm going to copy the link. Copy, I'm going to put it in there. Duty cycle, continuous duty. Boston, Massachusetts is calling me. I'm putting a link. And how do I do the QR code? How do I do a QR code? Where's the QR code? Choose, there's the text, interactive, themes. How do I do a QR code? Show responses live, so choose correct answer. No. Text color, no segmentation. Interactive. I got one person who responded so far. Where is the freaking comments? Edit. Choose answer. Multiple options. Oh, you know what I think I have to pay for? I gotta upgrade. Dadgummit. I've got a voicemail from Boston. Please come to Boston for the springtime. All right, I got 2 results so far. I think 2 results. What's the minimum size? Hey, Tom, could you briefly mention how XR ratios interact with motor current and OCPDs and what you think needs to be mentioned? So while we're answering this one, and I got the link up there so everybody can go up and take a look. So what is X to R, Willie? I got 3 people have chosen so far. X to R ratio is, hey, Chad Roberts in the house. There we go. X to R ratio is the ratio in a circuit. So whenever I do a circuit, if I would think about the overcurrent protected device and the current that it is called to interrupt, I would basically calculate based upon the fault current at the motor what the X to R ratio is. And what that means is I take the circuit back to that source and I look at what my total X is, what my total reactance is, and what my total resistance is. And if my X to R ratio is outside of how I list and test the product, then I need to adjust the interrupting rating of the overcurrent protective device. The only time that I have ever seen that play a role is when I'm close to a transformer because I have a lot of X. I can't remember what the X to R ratio needs to be, but there's a power factor associated with it, and I think it's 35%, something like that. I can't remember. Anyway, Willie, I would look at the manufacturer's instructions, and they'll tell you if your X to R ratio is greater than or less than a certain number, then you need to adjust the interrupting rating of an overcurrent device. My opinion is I have only seen that when my overcurrent device is right there on the secondary of a very large transformer that has a lot of X, and it adds to the overall picture, which for the X to R ratio, because you have to have a lot of X over to the resistance ratio. So Chad is saying now, okay, and I've got 3 people are saying that, boy, my neck is sore. I've got 3 people saying, I've only had 3 people even venture, and this is what do you say? Anonymous, right? So Chad's, and I saw somebody else mention this as well. Eli said a number 12. Vinny B says a number 12. So everybody seems to be tying in on a number 12. So here's my question, and I think I know how you got to a number 12. You did this. This is what you did. You went to chapter 3, and you said, all right, I've told you I've got 5 horsepower. My full load current is 16.7. 430.22 tells me my full load current needs to be at least 125%. So you took 1.25 times 16.7, 16.7, and you got 20.875. And then you came in here, and you know it's got to be copper. That's the other thing, is all conductors for motors have to be copper. That is a requirement in 430. Let's go to 430. Let's come up here to conductors. Where's my conductors? 430.6. It's going to tell me in here somewhere that it has to be copper. Where's it at? Where's it at? Copper, 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 copper. Nameplate value, torque. Where's copper at? Come on, guys. Here we go. Oh, terminals. Motor controllers and terminals of control circuit devices shall be connected with copper conductors. Motor controllers and terminals of control circuit devices have to be copper. So what you did was you went into this and you went to the 75-degree C column and you said, give me a value here that is greater than 20.875. 20 is not cutting it. 25 is cutting it because it's greater than 20.875. My question is, why did you go to the 75-degree C column? That's my fundamental question. When it could be as high as 200% of the nameplate, could be as high as 200% of the nameplate. If I look at motor circuit, a single motor, if I have a single motor, I cannot be less than 125%. The conductor, you're saying the conductor could be as high as 200% of the nameplate. I'm not, yeah, so I think what you're saying is because there's a minimum size of a 14, my motor could be fractional, and I don't know what you mean by that, buddy. 430.22 Edward. Edward. Oh, this is other than continuous duty. Yes. So conductors for a motor used on a short time, intermittent, periodic, or varying duty application shall have an ampacity not less than the percentage of the motor nameplate current rating. Yes, I would agree with you there. But I'm just going up to 430.22 proper, the parent text. It says conductors that supply a single motor used in a continuous duty application shall have an ampacity of not less than 125% of the motor full load current rating, and that full load current is coming out of the table, which is 16.7. It means the ampacity of my conductor. The last I checked, if I have a 90 degree C conductor insulation rating, ampacity is determined off of the 90 degree C column. Now, I can't exceed, from a termination perspective, I can't exceed the value in the 75 degree C column through that termination. So I have to protect it at that value. But I do not believe that I have to select a conductor and calculate my ampacity off of the 75 degree C column. If I have a 90 degree C conductor, I determine my ampacity based upon 310.15, which will give me how many conductors are in a raceway and what's the ambient temperature. I would use the 90 degree C column for ampacity. The termination has nothing to do with the ampacity of the conductor. The termination tells me, 110.14 tells me that if I have a number 14 conductor, the ampacity of that conductor is 25 amps. It can handle 25 amps every day of the week, twice on Sunday, 365 days of the year. But the termination, if it's 75 degrees C, I can't exceed 20 amps. So as long as my thermal overload is less than 20 amps, I'm good to go. And if I look at what my maximum setting is for this 5 horsepower motor with a full load current of 16.75, my maximum overcurrent protection is 20.875. 1.25, no, the full load amps is 14. So remember, my overload protection is based upon the actual nameplate data. So my 14 amps, 1.25 times that, I'm having an overload of 17.5 amps, which is less than 20. Now, because when I select my overload, I'm picking it based upon the motor. Now, I'm not saying what you're doing is wrong. I would do it the exact same way. I would go to the 75 degree C column, select the larger conductor. Because if I went by the 90 degree C column for ampacity, I could pick a number 14. And with that overload, I'm protecting the termination, less than 20 amps, good to go on termination for 110.14. I'm protecting the conductor, less than 25 amps, good to go on conductor ampacity protection. And I'm protecting the motor for its overload based upon the requirements for no more than 125% for the overload. So I've protected everything, and I've done it with a number 14. I agree with going to a larger size conductor, though, because if I go to a larger size conductor, if my full load amps was equal to 16.7 on the nameplate, 1.25 times 16.7 is 20.875. That exceeds the 20 amps for a 75 degree C column on a number 14. I would not be able to use a number 14 for that reason. I would have to go to a number 12. And then that would make sure that regardless of the full load amps that I have there, I'm protecting my termination and my conductor based upon a 1.25. Now, if I go to 1.4, which I'm permitted to do in Chapter 4, Article 430, I'm permitted to go as high in the overload protection. If I go to the continuous duty motor in Part 3, I'm permitted, if I have a motor that is tripping, where the sensing element or sizing of the overload device selected in accordance with what above is not sufficient to start the motor or to carry load higher size sensing elements. So I can go up to 140 for a service factor of 1.5 or greater. I can go up to 140% on the overload. And if I make that adjustment in the field, that 140% cannot exceed the 75 degree C column to protect the termination. The conductor is going to be protected. I'm not worried about that. But I'm worried about the termination. So I like the fact that most people who apply motors, all people that I have seen who apply motors, when they size the conductor, I think they are, I don't know that the code aligns with what is done, but I agree with it 100%. You need to pick the larger conductor, which is driven off of the 75 degree C column. You have to make sure that what's in the 75 degree C column is greater than the 125% of the full load amps, which is in the table. Keep in mind, the motor starter, all the equipment is fully rated for the application. And the overcurrent device that's upstream on the branch circuit, is that 80% rated? Yeah, but remember, I'm putting a very large, I'm using it for short circuit protection only. So there's a question for you. Do some investigation. I know I am doing my homework. I'm trying to do a complete analysis to understand the selection of the conductor, the selection of the infrastructure so that it doesn't have to change. So that whenever you change the overload to accommodate when the motor doesn't start, or to accommodate I changed the motor and I have a new full load amps on the nameplate and you need to change the overload to protect that motor, that you don't jeopardize the protection of the conductor, the protection of the termination of the equipment, and the protection of the equipment. You don't have to change your infrastructure just because you changed your horsepower in your motor, or you changed the motor with the same horsepower. Makes sense? So hopefully some of that made sense. Hopefully some of it stimulated you to go away and say, I need to take a look at what we do on motor protection. Freddie B, yes, Fred, they are. Motors are exempted from the small conductor rules. And the reason we know that is because in 240.6, not 240.6, 240.4, protection of conductors. In protection of conductors, if you go down to, so here's where your 240.4, conductors other than flexible cords shall be protected against overcurrent in accordance with their ampacity specified in 310.14 unless otherwise permitted or required in 240.4A through H. And if you go down, there's your small conductors. If you keep going past that, and right here in G, overcurrent protection for specific conductors shall be permitted to be provided as referenced in 240.4G. And right here for motor and motor control circuit conductors, it tells you that those conductors are protected based upon Article 430, parts 2, 3, 4, 5, 6, and 7. So that gets you out of the small conductor rules in Article 240. Hopefully that helps, Fred. It was a learning experience for me too. Chad Roberts. I agree, the wire can handle the amperage. Wires don't fall in the middle. They fall at the termination. Yes, and Chad, the termination in 110.14, basically, if I looked at chapter 3, when I land a 1-odd conductor, the conductor can handle, a 1-odd conductor can handle 170 amps every day of the week, twice on Sunday. The termination on 75 degrees C can only handle 150 amps. So I can use a 1-odd conductor, but I just can't pull more than 150 amps through it, right? The overload protection on the motor makes sure that I don't exceed that number. If this was a branch circuit, for example, my overcurrent protective device would have to be less than or equal to 150 amps to ensure, on a 1-odd conductor, to ensure I'm protecting the termination and the conductor itself. If it's the standard conditions of use, and I had a 1-odd conductor, I can't put a 1-odd conductor on a, what's the 240.6 standard ampere rating? Chapter 3, 150. If I go to standard ampere ratings, I have a 150 amp breaker. So I have 150. Let's go to an oddball. 130. Let's say I had a 1 gauge, and I had the ampacity of a 1 gauge is 145 amps, but I'm landing on a 75 degree C terminal. That means I can't exceed 130 amps through that termination. If I go to chapter 2, I don't have a 130 amp breaker. I can't go to 150 because then I would let 150 amps through that 1 gauge, that termination. I'd let 150 amps, which exceeds the 75 degree C rating of that termination. So I have to go down. I would have to put a 125 amp breaker to protect this circuit, unless I'm using 90 degree C lugs. And if I had it on a 60 degree C piece of equipment, then my breaker would have to trip at or below 110 amps to ensure that termination with that size conductor doesn't pull more current than what it's supposed to. And I know I'm not missing a meeting. All right. So, and that's my thought process on this motor stuff, is that when I look at sizing the conductor, and I've got a work in progress to try to understand this. And I'm going to show this. I usually do this more on another channel where I explore, but I'm going to explore here. If I look at this, for example, if I look at a 5, and Laurel knows I love spreadsheets. If I have a 5 horsepower motor, my nameplate says 14, which I took these off of actual nameplates of motors that are being sold on the web. A 208 volts, service factor 1.15. The full load current from the table is 16.7. 1.25 times that is 20.9. This is the exact motor we just did. If I use the 90 degree C column, which is this here, I would pick a number 14 because I have 25 amps of ampacity that is greater than 20.9. If I use the 75 degree C column, then I'm into a number 12. I have to increase the size of the conductor. With a 14 amp full load amp, my overload is set to 17.5. So I'm doing an analysis at 90 degrees with that motor, at 90 degrees, based upon 90 degree selection, I'm protecting the circuit. At 75 degrees C, I'm protecting the circuit. If I took my overload up to 140%, I'm still okay. I'm protecting the circuit because that's still 19.6. So what I did was I'm taking various motors of different sizes, nameplate values from the web that are being sold. And I'm just looking at this for the 1.25 overload protection, all of these motors based upon the 90, picking that overcurrent, picking the conductor based upon the 90 degree C, which is the ampacity for 90 degree C conductors, which in my opinion is what 430 says, 22 says. It says the ampacity has to be greater than 125%. I'm okay in the 90 and I'm okay at 75. Every single one of these, I haven't found one motor yet that the horsepower full load amps, if I based it upon the ampacity of the conductor, which would be the 90° C column, I am adequately protecting the termination below the 75° C column and the ampacity of the conductor. If I move it up to 1.4, I'm for the most part, so where I'm at right now is I've got 14 conductors I am not protecting at the 140% when I go by the 90° C column, and 6 conductors I'm not protecting when I turn my overloads up to 140% when I select it based upon the 75° C column. So I can argue I have more of a chance of protecting that conductor over the full range of the overload selection from 125% to 140%. And I hope everybody, if you're into motors, you're following me. If you're not, then you're like, I'm lost. That's okay. So, but what I did notice is that at the 140%, there are some, even when I select it based upon the 75° C column, I'm still not protecting the conductor at 140%, the termination, because I have to make sure I don't exceed the value on the 75° C column for that termination. So I'm still in my infancy. I'm trying to understand it, and I am analyzing, why do we pick the conductor size off of the 75? I've always done it. I was taught it to do it that way. And I'm sure whoever taught me was taught to do it that way. And when I go back in time, that language of 125% goes back to the 40s, at least as far back as I can go in the code. But I don't understand why. I just don't. I'm just trying to comprehend it. And I haven't found anybody who can. What they'll do is they'll go back to 110.14. And they'll say, well, 110.14 tells you, Tom, the conductor has to be based upon the 75° C column. And my argument again to that is 110.14 tells you what the maximum current is for the termination based upon the size. I need to protect that circuit at or below that number, and I get that done with the overload. I don't pick my conductor size based upon 110.14. I pick my overcurrent protection based on 110.14. I have to make sure that my terminal doesn't exceed that value on the 75° C column. And I'm not in the protection level right now. So I'm not, I'm looking for help. And I missed a bunch of, and I got to jump off. Willie Snyder, 240.4G. Yes, Willie, absolutely. That's what sends you back to 430. Hey, Steve, thank you. 430 is very complex indeed. Laurel, thank you very much. And thank you for all of your help in research. Every day, man, telling you, every day I'm going to learn something from everybody out there as well. Thanks for your time. Thank you, Vinny B. I'm going to go get that coffee right now. And then Eric, Eric, you're just coming in. Good morning from Idaho. Okay, buddy, and I must say goodbye. So hopefully we got something out of this. Is just the beginning of our journey in motors. I still haven't gotten to selecting the overload, looking at the equipment. We're going to look at Square D, Siemens, ABB, and Eaton solutions, try to figure out, are they fully rated? Are they 80% rated? Well, how do I determine the short circuit current rating? Oh my gosh, there is so much in Article 430, and motors are all around us. They're in our appliances. They're in our refrigerators. They're in our ceiling fans. They're even in our microwaves and our dishwashers. Motors haunt us every day. The more we know about motors, the better off we're going to be. See you next week. Thanks, everybody. Thanks, Michael Hufkin and everybody else. Take care, stay safe, and please stay healthy.